All right, geometry, let's get rolling into section 7.3. Here in the second half of chapter 7, things get a little bit tougher, and we start talking about the dreaded P word of geometry, which is proving. Now relax, we're not going to be doing any proofs at all here in the second semester, but these are ways that we could go about knowing for a fact that two triangles are similar, other than just saying that they appear to be. So let's take a look at what's going on here. Our first postulate in this chapter here is postulate 7.1, and it's called the angle-angle similarity postulate. Let me just take a second and talk real quickly about chapter 4, where we learned four ways to prove triangles were congruent. There was side, side, side. There was side, angle, side. There was angle, side, angle, and then angle, angle, side. So those were the four ways we learned in chapter 4 to prove that two triangles were congruent. Congruent means absolutely identical, same shape and same size. That is not what we're doing here in chapter 7. We're not trying to prove that two triangles are identical. We're trying to prove that they're similar. And if you remember our quick definition of that from earlier sections in 7.2, similar triangles are the same shape but different sizes. Okay, so postulate 7.1 tells us here that if two triangles have two pairs of corresponding angles congruent, then we know for a fact that the triangles are similar. So if we take a look at this figure down here on the bottom, we have a small triangle down here on the left-hand side, and I've taken one angle and given it one tick mark, and another angle, so there's the angle with one tick mark, and another one right here with two tick marks. As we look at the larger triangle on the left, we see that this angle right down here has the same one tick mark as this angle. So these two angles here are congruent to each other. Then two tick marks here and two tick marks here, that tells us that those two angles have to be congruent. So in this diagram, we can deduce already that these two triangles have to be similar to each other simply because they have two pairs of corresponding angles. There's the angle-angle similarity that we were looking for. Now, it's worth talking about a fact here that in actuality, these two triangles really have three pairs of congruent angles. We learned a theorem back, I think, in chapter 4 called the third angles theorem, and we'll see this illustrated in just a moment, but it said that if two triangles have two pairs of congruent angles, that actually means, and I'm going to erase this in just a second, but that actually means that the third angles in those two triangles have no choice but to be congruent as well. So actually, what we're really dealing with here is angle, angle similarity, because that falls in line with the idea that we talked about in 7.2 that said if two figures are going to be similar, all of their corresponding angles have to be congruent. But the fact that we're dealing with triangles right here allows us to take advantage of the fact that we really only need two pairs of congruent angles, and then it's a foregone conclusion that the third pair is congruent as well. So angle-angle is our first way to prove that two triangles are similar. So let's take a look at a couple of examples here, guys, and it's a simple yes-no in each one of these cases right here. Is each pair of triangles similar? So let's take a look at what's going on in number 1. We've got a small triangle on the left with a 41-degree angle here and a 78-degree angle here. To the right, let's take a look at what we have. Things have been flipped around a little bit. They're not quite in the same position, but sure enough, we have a 41-degree angle here. I'll put one tick mark there, and a 78-degree angle up here on top. These two triangles have two pairs of angles that are congruent. Therefore, the answer here to number 1 is yes, by angle-angle similarity. So we know for a fact that those two triangles are similar, just because they have two pairs of angles that are congruent. 41 degrees, 78 degrees. Seems really easy. So now when we look at number 2, let's take a look at what we've got. A 30-degree angle and a 70-degree angle. So I'll do one tick mark here and two tick marks here. And as we look at the second triangle, it doesn't look like it works out the way that the first one did. Our first triangle had 30 and 70. Our second one has 70 and 80. So the 70-degree angles are congruent. I can put a double tick mark here, but this 30 is not congruent to that 80. So it sure looks like these triangles do not have two pairs of congruent angles, and therefore you would think that we would have to say that they are not similar. But Things get a little bit more interesting here, guys. What we need to realize is that the angles we've been given might not necessarily be corresponding angles. And it's not going to take us very long to try to figure out what the third angles are in each of these triangles. Let's take a look at the first little triangle. We have a 30-degree angle and a 70-degree angle. Those add up to 100 degrees. And we know that the sum of the three angles in any triangle is always 180. So if we took 180 minus the 100 that we have for our sum, that leaves us right here with an 80-degree angle for the measure of the third angle in that first triangle. And now all of a sudden we realize, wait a minute now, we've got an 80-degree angle here and an 80-degree angle here, a 70 and a 70 right there, guys. That means that we have the two pairs of congruent angles that we needed. So number 2 is also a yes for the same reason as number 1. We just had to dig for it a little bit. They didn't give it right to us. So you got to be on your toes there. All right, let's take a look at this third example. And this is actually a diagram that we're going to see a lot of in our next section of notes on 7.5. Now, some of you are probably looking at this and are a little confused already because unlike 1 and 2, which maybe you understood okay, we don't have any angle measures here. So that can be a little bit of a problem. But let's take a look at what's going on. The other thing that confuses people about number 3 is it looks like we don't have two different triangles the way we did in 1 and 2. Well, let's take just a second and let me label all my points here. I'm going to go A, B, C, and then we've got a D and an E located right here. Okay, so do we have two triangles is the question. The answer to that is yes. One of the triangles, the one that everybody sees, I think, is the triangle that goes from A to E to B. However, there's a second triangle here, the larger figure, and that one is going to go from A to D to C. Okay, so there's actually a smaller yellow triangle inside the green triangle, and I apologize for using Packers colors there, everybody. That was a mistake on my part, and I'll try never to do that again. Okay, so we have two triangles, one in green and one in yellow, and the only way we know so far to prove that those two triangles would be similar is if they have two pairs of angles that are congruent. Well, to do this, we've got to go back and use the fact that we have parallel lines, that line segment EB right here is parallel to line segment DC. And we've got to use some things that we learned about parallel lines way back in chapter 3, which we did much earlier. And we need to remember that when you have two parallel lines like these, cut by a transversal like AD, you've got a pair of angles here and here that are called corresponding angles. Corresponding means in the same relative position, and both of those angles are on the top right of the intersection between the parallel line and the transversal. And when you have parallel lines cut by a transversal, your corresponding angles are congruent. So we know that angle AEB, which is an angle in the smaller yellow triangle, is congruent to angle ADC, which is the corresponding angle within the big green triangle. So that right there is one pair of congruent angles. Well, now if we take a look over on the right and we think about line segment AC as our transversal, we have the exact same thing going on right here. Angle ABE and angle ACD are corresponding angles between two parallel lines as well. So we could also say that angle ABE is congruent to angle ACD. And right there, everybody, there's the two pairs of corresponding angles that are congruent that we needed. So this one is going to be a yes as well for the same reason. The other thing, and some people see this right away and some people struggle with it, both of those two triangles share this same angle that I'm labeling up at the top with 3 tick marks. That angle right there, angle A, is an angle in both the small yellow triangle and the larger green triangle. So there's actually your third pair of congruent angles, but either way, we know that that one's a yes. Okay, so moving right along here, let's take a look at where we're at next. Okay, so in B, they're now asking you to solve for x here. All right, so let's see what's going on in this figure. You'll notice it does not say in the directions that these two triangles are similar. Now, I don't want you to think too hard about this, but we need to understand that if these triangles were not similar, there'd really be no connection between them and we wouldn't be able to solve for x. But we don't want to assume. if we take a look at angles, we've got an 80 and an 80 here, and a 55 and a 55. That right there tells us that these two triangles have to be similar by angle-angle similarity. So just a quick glance right there, didn't even have to do any math on the third angles, tells us that, that these two triangles are similar. We're trying to solve for x, which is a side length, and when we're trying to find a side length within similar figures, we've got to use a proportion in order to get that. So we've got to set things up. Now the one thing you'll notice that's interesting here, in the big triangle on the right, two sides have been given to you, the x and the 10. In the little triangle on the left, three sides have been given to you, the 4 and the 7 and the 8. And I did that on purpose just to make you think about how this one is going to set up. So here's what we're going to do. We're interested in finding x, so I'm going to start with that. There's a lot of different ways to set up this proportion, but I'm going to run with that. And my question now is, which of the three sides in the first smaller triangle, the 4 or the 7 or the 8, corresponds with the x, or is in the same relative position? And the easiest way to do that is to look across the triangle from x and ask yourself which angle is opposite from that. And the x is located across from the 80-degree angle. That means that if we started at the 80-degree angle here and went across from it, the 4 and the 7 are adjacent to it, but it's the 8 that's across the triangle from the 80-degree angle. So the x corresponds to the 8 in the first triangle because they're both across from the 80-degree angle. Okay, the only other option we have then for the second triangle is to use 10 as our next side. And the 10, you'll notice, is across from the angle that we didn't have the measure of. It's not across from the 80-degree angle. It's not across from the 55. It's across from the blank angle. So our blank angle in the small triangle is right over here, and the side opposite from that is going to be the 4. So the 10 on the right corresponds with the 4 on the left. You really got to pay attention to those and think about it. It's not simply the case of saying, okay, 8 is on the bottom here and 10 is on the bottom here, so those two sides must go together. That only works if the triangles are facing the same direction like this, but as soon as we flip one of those triangles around, it doesn't work out that easily. So let's take a look now. The x gets multiplied by the 4 to make a 4x. 8 times 10 is going to get us 80, and we're going to divide both sides by 4, and we're going to find that x is equal to 20. All right, so you got to be on your toes, especially when the orientation of your triangles flips around. Okay, second big part of our notes here. Theorem 7.1 is called the side angle side similarity theorem. Now you got to be careful because side angle side was also a test for congruence back in chapter 4. So let's see what this theorem says that's a little bit different. If two triangles have two pairs of corresponding sides proportional. Back in chapter 4, those corresponding sides had to be congruent, but now we're talking about proportionality. So if they have two sides, pairs of corresponding sides proportional, and their included angles, meaning the ones in the middle, are congruent. So this is important, guys. Sides have to be proportional, angles have to be congruent. If that happens, then your triangles are similar to one another. Okay, so let's see what this one would look like here. Now again, these are yes or no questions. Are the pairs of triangles similar here? Now, if we take a look, this first triangle only has one angle given to us, 35 degrees. We don't know and we can't figure out the measures of these two angles right here, so we can't go for angle-angle similarity. We're going to have to try side angle side. The first thing we're going to do is figure out the measure of this third angle right here because two angles were given to us. 80 plus 45 makes a total of 125 degrees. If we subtract that from 180, that is going to get us, let's see here, 55 degrees for the measure of the third angle right here. So that's going to be 55, and we got it. What we can see is that this 35-degree angle here doesn't match up with any of those three angles right there. We don't have any known angles that are congruent, so for this first one here, we'd have to say a no. That's the first time we've seen this one here. Now, if we take a look at example 2, You'll notice that's almost the exact same setup as what we just did in number 1, but one of the angles that I gave you was just a little bit different here. So playing around with this one here, we've got an 80 plus a 65. That makes a 145. And if we take 180 minus that 145, that gets us now 35 degrees for the measure of our third angle. And sure enough, that angle is congruent to this one right here. So we do have the one pair of congruent angles that we needed. But for side angle side to work out, we need to have a proportional relationship between our two pairs of corresponding sides. And that's usually not something you can tell just by looking at the diagram. So we've got to set up a proportion and see if it works. Pick a side in the first triangle. I'll start with the 12. And that corresponds to the 10 over here in the triangle on the right. If for no other reason, I know 12 is the shorter side on the left, 10 is the shorter side on the right. And now we'll do the longer sides. 18 on the left, the longer side, would have to correspond to the longer side on the right, which would be 15. So this is our proportion. Let's find out if it works. The 12 gets multiplied by the 15, and that's going to get you a product of 180. The 10 gets multiplied by the 18. That gets us 180 as well. So the fact that those two cross products are equal means that we have a proportional relationship between two pairs of corresponding sides. So that tells us that in this setup here, in number 2, we've got two pairs of corresponding sides that are proportional and a pair of included angles that are congruent. So the answer to number 2 is yes, those two triangles are similar, and we would say that they're similar by side angle side similarity. So that's our answer there. So two good examples there. One where it didn't work, one where it did work. All right, and our last theorem here of this section, theorem 7.2, this is side-side-side similarity. And you could probably figure this out just based on the name. If two triangles have three pairs this time, three pairs of corresponding sides that are proportional, then those two triangles have to be similar. So this one says nothing at all about angles being congruent. It only deals with the proportionality of all three sides. So let's take a look at two examples right here. Now, in these problems, especially this first one, I drew these triangles in a really vague way so that it wasn't clear which side went with which. And I did that on purpose because I want you guys to see the way that we're going to handle this. In our first triangle, we've got side lengths of 12, 16, and 20. The second one has side lengths of 12, 9, and 15. What you really need to pay attention here is the order of your sides, smallest, middle, and largest, and you need to make sure that you're putting the right ones together. I like to go smallest to largest. So as I look at this first triangle, I'll call this triangle number 1, the smallest side in that triangle is 12. Now I'm going to go over here and look at triangle number 2, and don't just say 12 has to go with 12 because they're both in the top left-hand position. All right, what we need to do instead is say, all right, 12 was the shortest side in the first triangle. Now I need to look for the shortest side in the second triangle, which is 9. Let's go middle. The middle side in the first triangle is 16. That would have to correspond to the middle side in the second triangle, which is this 12 right over here. And lastly, the biggest side in the first triangle is 20. If this was going to work, that would have to correspond to the biggest side in the second triangle, which is 15. So the question, and there really should be question marks here, is are all of these ratios equal to each other? Do we have a proportional relationship across the board? Well, again, there's a couple of ways to do this, but probably the best thing to do is to try to simplify each one of these ratios. 12 over 9, we have a GCF of 3. So dividing by 3, our numerator becomes a 4, and our denominator becomes a 3. All right, 16 and 12 in the middle have a GCF of 4. 16 divided by 4 is 4. 12 divided by 4 is 3. And lastly, 20 and 15 have a GCF of 5. So let's divide that 5 out. 20 divided by 5 is 4. 15 divided by 5 is 3. And what we can see very plainly right here is that all three of these ratios simplify to exactly the same thing. So, for that reason, everybody, we can say that these two triangles are similar. So this is a yes, and we can say that by side-side-side similarity. That only works because all three of those ratios came out to be the same thing here, 4 to 3, 4 to 3, 4 to 3. By the way, what you just found right here, guys, you just found the scale factor of the larger triangle to the smaller one of 4 to 3. It's the ratio of your two corresponding sides when your figures are similar. Okay, and let's take a look at this example here. Now, I really didn't leave myself much room, so let me see if I can do this, guys. I'm going to try to take this and copy it, and let's see if I can make a new page right here and paste that right here and see what's going on. I think I missed a side there. That looked like it was a 19, I think, in that bottom right-hand corner there, guys. So let's put that 19 right there, and let's see what we've got. Okay. So let's check for proportionality. All right, shortest side in the first triangle is 21. Shortest side in the second triangle is 9. Middle side in the first triangle is 28. Middle side in the second triangle is going to be 12. Keep going now. Longest side in the first triangle is 42. Longest side in the second triangle here is 19. Okay, I'm going to show you how to do this one slightly differently here. If we wanted all of this stuff to work out the same, we could try simplifying ratios, but this one's less obvious. So what we're going to do instead here is to try, sorry everybody, let me see if I can do that. Okay, what we're going to do is try to do some cross multiplying just on two of these at a time. I'm going to multiply here the 21 multiplied by 12 and then the 9 compared to the 28. And let's just see right there if that works out. So grabbing my calculator, 21 times 12 gives me a product of 252. The 9 multiplied by 28 gets me a product of 252 as well. Now what that tells me, because these two cross products are equal to each other, I know that these two ratios are proportional. They are equal, and that means that we've got two pairs of corresponding sides here that are proportional. This is a good start, but in order for all of this to work out, it wouldn't need to work on just two of them. It would actually need to work on all of them. So I'm going to take a second in blue now and focus on what's going on right here with this set of ratios. Here we would multiply the 28 multiplied by the 19, and we would want to make sure that that's equal to the product of 12 and 42. And let's see what happens now. We certainly don't want to assume that just because it worked once, it's going to work the second time. 28 multiplies by 19 for a product of 532. And on the right, 12 multiplies by 42 to make 504. And right now, guys, the plot thickens and everything falls apart. In this case right here, these two cross products were equal to each other, but here they're not. 532 is clearly not equal to 504. So what this means is we do not have side-side-side similarity here, because while two of the ratios were proportional, the third one was not. So the answer to this problem here is going to be a no. It wasn't enough just to have one pair of ratios that worked. You needed to have a second one there as well. And because they didn't all work, our answer to that one is no. These triangles here are not similar. All right, guys, that's a wrap on 7.3. Let's give that homework a try and see how everything goes. Good luck.